For the engineers, this was always going to be a bridge over troubled waters. Yeah, I know, sorry, but it was. Just getting started was going to be a huge engineering challenge. In fact, when they began, they still didn't know how they were going to lay their foundations. The sea here is 65 meters deep. It's a challenge in itself, but at the bottom, there's nothing but sand and silt for hundreds of meters down. There's no solid bedrock. And no solid bedrock means no solid foundations.
Solid foundations are, of course, crucial to any structure, especially when they're shaken by frequent earthquakes. Combining a sandy seabed with seismic activity results in a relatively little-known danger from earthquakes, called liquefaction. In a tremor, soft, wet ground literally turns to liquid, which really is as bad as it sounds. Nobody in the world had ever before set out to build a bridge in these conditions. The engineers came up with a solution that seems to defy logic. But first, why does a tremor turn sand and water into a liquid? I've created an earthquake machine to replicate the conditions at the bottom of the Gulf of Corinth. This engine is going to play the part of an earthquake. The sand and water can play themselves, and to get a bone-shaking feel for the problem, I'll be the bridge itself.
If you add an earthquake to loose, wet ground, something pretty strange can happen, as I shall now demonstrate. Here we have the loose, wet ground. It's sand with water, but it's, you know, solid enough. Standing in here quite happily. OK, if we're ready then, chaps, take it away. Now, my earthquake is starting. It is really very loud and very shaky. And straight away I see water coming to the top. In fact, I think I'm starting to sink. That's a lot of water. Clearly, what's happened is, apart from being deafened, I've sunk. It isn't just that the water's on the top, man. I'm in the ground. So I need to find out what's happened. And to do that, I need to get out. And that's not very easy. OK, I am actually part of the ground now. Yeah, OK. There's no approved technique for doing this, obviously, because... hold on. Yeah. Obviously, in the Western movie version of this, I'd get my horse by the side of the quicksand and he'd pull me out with the reins. OK.
The ground holds me up fine before the earthquake. Then it turns into quicksand. As it's shaken, the whole thing changes from solid to liquid. It liquefies, and I sink. Geotechnical engineer Stuart Haig explains that the key is that the sand is wet.
When the sand particles are shaken, the spaces in between them, or the pores, try and get smaller, and the water that's in there gets squashed and the pressure goes up. Once that happens, whatever's standing on top of it, whether it's you or a building, sinks into the ground.
Combine wet sand with seismic shocks, and it's a killer. When a huge earthquake hit Kobe Harbor, Japan, in 1995, over 6,000 people died. It measured 7.2 on the Richter scale. Sure enough, the ground was sandy and full of water. When the mix was shaken and stirred, the result was catastrophic liquefaction. Literally, the previously solid ground became liquid. Ordinarily, engineers can drain the sand to get rid of the water, or compact it so that the water is squeezed out. None of this was possible in the Gulf of Corinth. You can't drain the bottom of the sea, and there's sand to compact up to 500 meters deep, an impossible task.